Yeah, it's been a really great week for me. And I also want to just thank all the participants. You know, these things, you know, the success of these things really depends on, you know, kind of like the participants' involvement. And I feel like people have really been putting a lot of work into it, and it's been kind of very inspiring for me. So thank you, everyone. So when I was in primary school, the custom was that on the last week of term, people were allowed to bring in their toys. So I know that people have been patiently attending all these talks about, you know, vector bundles and isocrystals and whatnot, but a lot of people in the audience, what they really like to play with is actually Galois representations and p-adic Hodge theory. So hopefully we'll be able to do that later. But there's still a tiny bit of housekeeping to take care of. So remember, in the last lecture, I introduced this notion of a universal connection, and slightly technical point was that it was universal once I fixed this point in the fiber. And I gave some example. We saw it quite a bit in depth one, and what I'm going to do now is add some structure to this. Observe that it has some extra structure. And I'm just going to kind of state these very useful results, but I won't really talk much about the proof. So I've already kind of claimed that it exists. I'm being a bit vague here about whether I want to think of it as an algebraic connection over my curve x or y, or as an isocrystal, so something which is living on this tube, an analytic object. But I'm just going to use the same notation for both, because there's an algebraic object which you can analytify and you get the analytic one. So the first result is that this thing has a Frobenius structure. Proof. Going to be a bit of a black box, but basically the idea for why this is true is there's a theorem of Chiarolotto and Lastum, which says that, which is kind of slightly related to the constructions which go into the proof of the unicity of Coleman integration, is that this is basically that this is an equivalence of categories from the category of unipotent isocrystals on Y to itself. This is some kind of souped up version of this fact that m-1 was invertible, which we needed to compute common integrals in practice. And this implies that if you have a universal object, that the pullback is also universal. So having a Frobenius structure is just saying you have an isomorphism of two analytic connections. On the other hand, this universal property which these things satisfy is a thing which guarantees the existence of lots of morphisms. So it just means you can get a morphism one way, you can guarantee that exists by one universal property, and then you get a morphism back the other way, which inverts it, which you can guarantee exists by the other universal property. I won't go into too much detail on that. But maybe I'll just remark, I mean, how do you, let's just remind ourselves what the Frobenius structure was. So a Frobenius structure, remember, was an isomorphism. So I guess I was in the habit of doing the kind of the inverse Frobenius structure. Pull back. But we already actually did this for an affine curve using this theorem of Kim, that you can actually write this locally just as a matrix, lambda n, And then you have that matrix of one forms, and you can just apply Frobenius to each entry. And then the identity which you're asking to be satisfied is exactly that. Do this and apply F, so that's equal to df plus this. So, and then if you think of the connection we wrote down before, that was some block matrix whose entries were given by explicit differential forms. And so this actually just becomes some p-adic differential equation, which, for example, for a hyperelliptic curve, you can plug Kedlai's algorithm into the bit of work. So it's really, I mean, it's a very complicated object, but there are lots of situations where you can actually compute it. So the next thing I want to do is I want to define a Hodge filtration. I'm going to define what that means, talk about Hodge filtration on a connection, and then I'm going to say something about how it's defined, and then we're going to try and compute it in an example. And I know with this, particularly once we've introduced these universal objects and this En nabla n, there have been kind of a lot of consecutive definitions which have come up. And actually, I was thinking about this, it reminded me of once when I was in a conference, and there was kind of a very important figure in the field, and he was giving a talk, and it was something very cutting edge research. I mean, much better than all this. And he just kind of cracked on straight away and just made loads of definitions and constructions and kind of sketches of things. And I think people got a bit lost. And then at some point halfway through, another kind of big name in the field just said, "Carlos, why are you doing this?" Which captured the mood in the room. And then he explained it a bit. So, I mean, maybe some of you in the audience are thinking at this point, why are we doing this? So the reason to do this is because once we have a Frobenius and we have a Hodge filtration, and it's going to turn out that we're in good shape to speak about relations to Galba representations. So the definition is that a filtered connection is a flat connection. So now we're in the algebraic category. B nabla on x over k together with filtration, which usually right. And we want it to be a decreasing filtration. Maybe I'll write it I. Which we want to be also called exhaustive and separated, so that we get the whole of V. And eventually it's just going to be 0. And so it's very important. So earlier in the last lecture, I was talking about filtrations by connections, but we actually want this to be a filtration which doesn't respect nabla necessarily, but it has the property that when I apply the connection, I don't move too far down. And this condition is called Griffith's transversality. Which is maybe the name is a hint that there's kind of some serious algebraic geometry going on. So this turns out to be kind of a condition on a filtration, for example, Hodge filtration on a variety, which kind of guarantees that it can vary in power. Kind of there's some geometric reason why it's the right notion. But the reason I'm introducing it is just for this theorem. which characterizes this Hodge filtration, this filter connection structure we want to put on En. This is due to Majid-Hadian. So we have a flat connection, En nabla N. En nabla N. So it's, I guess, structure on which what do we want it to satisfy? We want that when we take the fiber, so remember we have our distinguished point En, which was in the fiber, I think, of B, some point B, so remember we had B and xk, and we had this distinguished point, which was part of the universal property, which was in the fiber at En. And we want this point to be an F0. And then the other condition we want is I guess we saw this in the example that I gave at the end where we had an affine curve. You think about remember we constructed this universal connection essentially what we just did was we constructed some quotient of the tensor algebra on the dual of the Durham cohomology. It was a free associative algebra with some basis, but really the basis was just coming from choosing a basis of Durham cohomology. So it turns out that there's an exact sequence like this. Goes from this to En minus 1, 0. It's not, in the case we saw at the end of the last lecture rather, this morning, this was injective, but in general it doesn't have to be injective. Already for n equals 2, it's not. And the condition is that this is strictly compatible with the filtration. So sorry, this should be tensor OX. So where the filtration on this one is coming from the fact that Durham cohomology is filtration. And we call this filtration structure, we call it the Hodge filtration, universal connection. So maybe to make this a little bit more concrete, I mean, how would you actually compute this in an example? Because I mean, you can compute it. So let's take X to be a projective curve. So then this E1 will essentially, I mean, when we described it, we chose some explicit basis differentials for Durham cohomology, but really how we described it as a vector bundle on some open affine Y was just a direct sum of the trivial vector bundle with this thing tensored with the dual of Durham cohomology. And actually, it turns out that you can check that this direct sum decomposition, at least if I choose, when we choose our basis differentials, if we choose reps omega I, say such that maybe the first, such that some subset of them actually form a basis of H naught omega, then if we do that, then this F naught of E1 will just be compatible with this direct sum decomposition. So maybe I should just, I haven't really discussed much about, so we've discussed quite a bit about the Hodge filtration just as a filtration on the Durham cohomology. It's come up in Samuel's lectures as well, but let's just remind ourselves of the numerology that we have on Durham cohomology. We have H naught x omega to H1 Durham x over k to h1 x over x. And so the numerology, which is the convention in the subject, is that this is f1, and then everything is f0. So on this, everything's in f0. So when we dualize, then we get an f0, which is be thought of as functions on. And then H1 Durham dual modulo, the thing that we've actually spent a lot of time thinking about is space of functionals on differentials, which we can just think of as 1 Durham of x over k dual modulo f0. Okay, so depth 1, it seemed very simple. Turns out for depth 2, it's slightly more complicated to calculate. And well, actually, what we can do is we just write down charts. I mean, oh yeah, sure. This one? Ah, yes, thank you. So yeah, I mean, we're trying to describe a subbundle of a vector bundle. So one way to do that, which is the kind of approach I've been taking, is you just take affine charts where you trivialize your vector bundle, and then take affine charts where you trivialize the subbundle, and maybe there you could have to refine your cover, and then you describe the maps on each chart, and then check that the transition functions line up. So you can just describe it in terms of cocycles. What does that mean explicitly? So we have some fixed y, which is kind of like a distinguished choice of u alpha. And on that, well, we'll choose y such that we have some decomposition of this vector bundle, not thinking of it as a subbundle, just like this. And then we can describe the map y to naught. So maybe I'm going to introduce some notation. So I'm going to define this now to just be V Durham. This, oh, sorry, not this one, this one. So this is V Durham is going to be my notation for the dual of Durham cohomology. And maybe I'm going to define V Durham just for this talk to be, turns out to be the right thing to do. V Durham dual tensor 2 modulo the image of V Durham. And then it turns out that so this thing also has a Hodge filtration. That the graded pieces of the F0 of E2 are going to be given by this naught of V tensor OY F0 of this, sorry, this V Durham 2 tensor OY. And then E2 is going to be given by the direct sum of OY, the whole of V Durham tensor OY, and the whole of V Durham 2 tensor OY. So what that means is that we could just describe, so we're describing this map from F0 V2 into E2. We've got a trivialization of this and a trivialization of this, but maybe they're different trivializations. And so the map gets given by some matrix, which I'll write as J. Sorry, I didn't finish my sentence. So this is F0, and then E2 we're describing as OY plus V Durham tensor OY plus V Durham 2 tensor OY. Then our matrix will again just be some unipotent matrix with 3 blocks where this is now my computation earlier, this is some 0, and then we have 2 things here which we don't know what they are. what are these blocks? For example, the idea is meant to be that this is this corresponds to O of y, this corresponds to F naught of beta ram, tensor with O of y, and this is F naught of beta ram 2. Yes, and then this is O of y, this is beta ram. Okay, so maybe let's actually come up with some names for these things. Let's call this one H and this one G. And then remember, we have we described the extension of this big vector bundle here to the whole of X by some charts. So remember, E2 is given by U alpha, lambda alpha, G alpha beta. And so maybe let's say that our y was U alpha. So then the condition that J actually defines a subbundle. So this J now locally on Y is defining a subbundle of E2 restricted to Y. And when does that extend to a subbundle of X? That's the question. Is exactly just the calculation that for all beta, this matrix, G alpha beta, when I compose it with J as entries in O of U beta. So a priori, it might have some poles, but the condition is that we don't get any poles. Well, I felt I should go into some detail on these kind of things. Maybe it seems somewhat prosaic for Friday afternoon, but I said in the title that it was going to be from theory to practice. So I thought I should put that into practice. So I don't want to give I wanted to give an example. So for genus 1, nothing interesting happens because E2 will just be E1. And then for genus 2, I guess the dimension, the rank of E2 is going to be 1 plus 4 plus 15. So it's going to be a rank 20 vector bundle. And maybe these blackboards are a bit too short to write it down. So I'm going to take a quotient of E2 on this curve. So remember this is I'm really studying modular curves here, because this is x0 to 37 again. So take a quotient, which I'm going to call E nabla, which will be, it turns out to be the right quotient for applying quadratic Chabauty to this curve. So remember, actually, we had this discussion about when does a 2 unipotent connection actually extend without poles? If we write it just in terms of, remember we had connections like this. And we said, when can we extend it? Maybe after choosing some eta to a connection on the whole of X, and the condition was exactly that omega 1 omega 2 is equal to 0. And we've picked a basis. You might remember we saw that this was a basis, these eta i's, Aramco-Molgi. And it turns out, if I haven't fudged the numbers, that the matrix of eta I cup eta j is exactly this symplectic matrix which Jennifer was talking about last. So that means that we can take lambda equals, we can come up with a rank 6 quotient of this rank 20 vector bundle, which is given by 0. And then here it's eta 3 minus eta 4 minus eta 1 eta 2. And well, it turns out that, the reason that that this works is exactly that, eta 1 cup eta 3 minus eta 2 cup eta 4 is equal to 0. And well, actually, the reason I know that we don't have to add a differential form here again is I'm going to say it's the Atkin-Lehner involution, but really this is very general. This is just the hyperelliptic involution. That's just a side remark. Okay, so then what are our charts? Well, I think we more or less did this calculation last time, if I haven't messed it up. We get F2 equals this, and this thing equals minus y over x squared. And then this is from kind of, I think, was the notation we had last time or somewhat similar. Then we get a chart which is given by, say, G alpha beta. So it's just the transition from the chart at 0 to the chart at infinity, given by 1, 0, 0, 2, F3, 2, minus F3, 0, 0, 1. And we have 1 still along the diagonal. And this turns out to be 0, actually. We can check that we can take this to be 0. And then, okay, so then now we want to work out what our matrix J is. And again, by calculation implies we can take J to be equal to just 1, I1, I2 with zeros everywhere. And what does that amount to? So that amounts to essentially computing what these expansions of F2 and F3 look like at infinity using this description here and just seeing that their poles cancel out. So that's, hopefully, if I have time at the end, we'll come back to that example. And again, more or less all examples where, you know, this, I mean, well, it's not, this is kind of something which is well understood, but all examples where this Hodge filtration has been computed, it's kind of this order of magnitude of difficulty. So it doesn't, at least in terms of what's being done at the moment, it doesn't get any more complicated. Maybe it's worth making a comment which just echoes what Samuel was saying this morning, that these, as hopefully they'll say at the end, these formulas, these numbers for this Hodge filtration, this equation I wrote down for the Frobenius structure, they do tell you very explicitly what the quadratic Chabauty functions, which we know should exist, should look like on modular curves such as, well, so, which we know exists, as Samuel will explain next week, on curves like x naught plus of p and x non-split plus of p. But I mean, the way these formulas have been defined have involved lots of choices. We choose some basis, and then you can write down some charts, and then you can find solutions to this. And so again, I mean, the question is, I mean, from this perspective, this very computational perspective in some sense I've given on the subject, is there a good way of choosing this, which allows you to link to the geometry or the arithmetic of modular forms, modular curves? Or maybe it turns out that the other perspectives on the subject, such as the one which Samuel described, are actually a better way to do that. This is what we've described here is kind of like a computational approach, not a conceptual approach. Okay, so that was an example. So now let's get to Gauss representations. So what have we concluded? What we've concluded is that En nabla n has the following structure, what's called a filtered F isocrystal. So filtered F isocrystal on X over ZP. The filtered connection on X over QP together with a Frobenius structure on its analytification. So what's its analytification? So you can think of this connection as a connection on the Berthelot generic fiber of the formal completion of X along its special fiber, and then you're asking that that is an overconvergent isocrystal which admits a Frobenius structure. So what we've shown, well, it's rather what these two results I stated have shown, is that En nabla N admits an F isocrystal structure. Sorry, filtered. So a nice example of a filtered F isocrystal is a filtered F isocrystal just on ZP. So this is what's called filtered phi module. So that's a finite dimensional vector space together with an automorphism called Frobenius and a filtration like the one I described, so decreasing, separating, exhausting. I think I called it an exhausted filtration. Maybe it's how we're all feeling after this hard work this week. Exhaustive filtration. Written FIFD. So filtered F isocrystals have lots of nice properties, and one is that you can pull them back. So in particular, given filtered F isocrystal, I'll just write it as V nabla on X and a ZP point. We get filtered phi module. So in particular, En nabla N is defining a map from QP points of X to filtered phi module. And so this is actually the first time in this, all these however many hours, 5 hours or whatever it is I've been talking, where I'm actually going to mention rational points. So maybe it's easy to forget that actually, why am I here? I'm supposed to be talking about rational points. So what we want is we want some kind of obstruction to a p-adic point coming from a rational point. And all I've given you is I've described in some detail, and even if maybe not really enough, how to get from a p-adic point to a filtered phi module. So how has that helped? Well, the idea is that we want to port the question over to this side. So what does it mean for a filtered phi module to come from Q? Well, what it means is that it should come from a GQ representation. So this is my notation is always going to be that GK is going to be the Gower group. So how does this work? So you can restrict a crystalline GQ representation to a crystalline GQP representation. And then it turns out there's a way you can get from that to a filtered phi module, and it's almost an equivalent. So if I add some other words, be admissible, then actually this ends up being an equivalence, and there's a functor this way called dCris, and there's a functor the other way. His name I've forgotten. So, and in fact, the behavior of this functor is the definition of crystalline, so it doesn't really matter so much. What the crystalline means, you can think of the functor as kind of the definition. Okay, so that was came a bit out of nowhere. So as I said, I know some people in the audience know far more about this subject than I do, but maybe for people who haven't seen this before, kind of how should you think about it? I would say a good picture to have in mind for the purposes of this course is something called The Lion, the Witch, and the Wardrobe. I don't know if any of you, this may be more of a familiar story in the UK. It's a kid's book in the UK. So the story, I mean, the name kind of contains most of the story. So there's these kids, and I think they're at the grandparents' house or something, and they find this wardrobe and they open it and they go through, and then suddenly they're in this kind of magical world. There's a witch, there's a talking lion, James McAvoy is a centaur or something, I forget the details. So it's really, the point is that this is like we started out in some very interesting category, but we were just doing linear algebra really. And then, we open this door and suddenly we've got all this magical structure. So yeah, let's just say it's a black box. But I mean, that's going to be our abstraction to rational points. And actually, this is how we've used this method to find rational points in practice. Yes. So, I mean, there's some other, actually, it would be more accurate to say that we have a map from X of Q to GQ reps. And then for all primes V, we have a map from X of QV to GQV reps. And actually what we do is not, so we need some information, which this also came up in Jennifer and Samuel's talks, that there are these local conditions and local constants. And those are coming from describing these maps at other primes. And that's a very interesting story. So Jennifer mentioned this paper with that I have with Alex Betts, which describes a little bit about this map. And actually, I remember during this week, again, even though this course isn't really anything about modular curves, this paper which we wrote, it became very complicated and ended up being very long, 120 pages, but it actually all started from a calculation on X0 of 37. So which I'd forgotten until preparing my notes this week. So, so maybe actually I do work on modular curves. Okay, so let me describe a bit more about exactly what this map is. Oh, from points to Gower representations? Yes, so so well, I suppose strictly speaking, the map is not really to Gower representations, but it's Gower representations with some additional structures, which I'm just about to describe. But so for P, they are injective, and I think this was actually probably originally proved by Mochizuki in the 90s, but maybe now there are other ways of proving it. And so actually for L not equal to P, this was exactly what this paper of mine with Alex was about, was showing that this map for L not equal to P was injected. And the reason it came about was where you get maps for each n, kind of like depth n, and I noticed that for x naught of 37 at the prime 37, it wasn't injective, and this was kind of surprising. Yeah. So it's just a GQ representation whose local just goes through P. Yeah. I mean, we also want to impose some conditions at other primes, but I'll add that later. Yeah. So just an observation is that this idea that we kind of try and describe rational points by, so I mean, what's the idea is that we want to look at QV points where their image under this map, their Galois representations come from a global Galois representation. One way to think about it is that we're trying to port local global principle for Galois representations, the local global principle for rational points. And I mean, so another example of this very similar ideas, which has been very powerful, is something called the Lorentz-Venkatev method, relatively recent, which has done this where, I mean, some of the techniques which I've been describing in previous lectures actually come up a lot in their work, but actually how they vary their Galois representations is quite different. So we're going to vary our Galois representations unipotently, and they vary them reductively. So to explain kind of the objects that we consider here, it's not quite spaces of Galois representations, but it's something called mixed extensions. This is just some terminology which is convenient. It's some kind of, I guess, unipotent or iterated generalization of the notion of an X group, which I was discussing earlier, and an X1 extensions of two objects in an abelian category. So maybe to avoid being kind of getting too much into general nonsense, let's just do this for representations of the group G. So like B naught Bn. The representation, maybe let's, again, to avoid too much generalizing, so QP representations of group G. And in practice, we're going to want them to be continuous and topological. That won't matter. So a mixed extension with graded pieces V naught up to Vn is a G representation M, maybe let's call it E, together with two bits of data. So the first one is a G stable filtration. V naught, V1, Vn plus 1 equals 0. G equivariant isos from the gradeds to my fixed graded features. So I'll give an example before I go on. Sorry? Oh, sorry, what note did I change? Ah, yeah, sorry, I went GI. Yes, you're right, absolutely. EIs. So yes, well, yeah, I should have called yeah, it should. Aesthetically from GIs. Thanks. So I'll give a few examples. So, well, first of all, maybe let's just, oh yeah, maybe just concretely. If E is a extension with graded pieces, I'll just write them compactly like this, VI. And let's say that rho I B to VI is the rep associated. Then we can describe the action of G on E really, this is all just some language for saying that the matrix of G acting on E is at this form. What we're doing. Okay, so now I want to say when I think two mixed extensions are equivalent. So an isomorphism of mixed extensions with graded pieces. Graded VI is a G equivariant map. Say F from E to E prime. So actually, it's going to be an isomorphism, so say that, which is strictly compatible with filtrations. And also with the alpha i's and the alpha I primes. So that is to say that alpha I prime, the isomorphism from VI to this graded piece of EI is exactly the one you get from taking the inverse of this. Or rather, I guess, applying alpha I. Okay, so then I'm going to say that M, well, I'm going to have lots of different notions of isomorphism class of mixed extensions, but let's just fix one now. So MG VI is mixed extensions with these graded pieces, modulo isomorphism. So now I'm going to give an example. So when n equals 1, what does this look like? So you can check that mg of v0 v1 is exactly the same as an extension, a category of G representations of v0 by v1. So remember, an extension we could think of as a short exact sequence of G representations up to isomorphisms of short exact sequences. And that short exact sequence exactly gives you the mixed extension structure. The isomorphism between. Yeah, so yeah, maybe I should just spell that out. So remember, alpha I was an isomorphism. I think I said it was from VI to, we could say, the isolated piece of E. And then alpha I minus 1 was an isomorphism from this. Maybe let's call that alpha I. And then alpha I prime was an isomorphism from this. And then we said this isomorphism was strictly compatible, so we get M at F, and we just want that. So I should say all these definitions, mixed extensions, are just kind of the natural, do the most obvious thing definitions, and actually some of the other definitions, which maybe we'll see later, of definitions which I first came across. I mean, I think they'd appeared in other contexts, but not for Galois representations. I first came across in a paper of Nekovar on p-adic height pairings. I strongly recommend, I think, Jan and Samuel and Jennifer can attest to my proselytizing about that paper. So this is maybe a chance to see kind of some of these ideas in other contexts, other applications. Okay, so I've done all this for G representations, but actually this notion of a mixed extension would have made sense in any abelian category. And we can also define the notion of a mixed extension of filtered phi modules and everything works exactly the same. So maybe let's just give a nice example now. So remember, if we remember this connection E1, nabla 1, so this was going to give us actually, this had a Frobenius structure. If you remember that Frobenius structure, or rather its inverse, was given by this block matrix, which was 1, the matrix describing Frobenius acting on Durham cohomology, and something which was varying with the point, but this was this was constant. So actually E1 was giving us a map from QP points of X to extensions of filtered phi modules, or same as mixed. I'm going to call M fil phi, so that's my notation for mixed extensions of filtered phi modules of QP by this thing I was calling V Durham, which is just, that's H1 Durham dual. And remember, this is just the same as extensions. So how do we classify these things? Well, actually, we're going to see something very familiar come up. So suppose we have an extension, filtered phi modules. So that's, let's say we've got some element here, E, then E maybe, then it's represented by some extension like this, filtered phi modules. And so it turns out there's a unique splitting of this extension the phi module. And that's again related to the fact that the eigenvalues of Frobenius this are not equal to 1. So we could call that splitting maybe S phi. On the other hand, we could choose a splitting which respects the Hodge filtration. So if you think, I mean, filtered vector spaces over QP, I mean, every filtration on a QP vector space can be trivialized, so you get a graded vector space, just choosing a basis. SH respecting SH. So then S phi minus SH gives us an element now of V. So we're in, we want to classify extensions, and now these things both, sorry, I guess S phi 1. We now have something which just depends on V, so we seem closer to classifying the extensions. And this was canonical. This didn't depend on a choice, but this did depend on a choice. I mean, we could choose different splittings respecting the Hodge filtration. But if we choose a different, if SH prime is a different choice, if you think about it, they're different. SH of 1 minus SH prime of 1 is actually going to define an element of F0 of Vitoram. Because they have to agree in QP, they're both just 1. And then they both have to lie in F0. And actually, that's the only ambiguity is changing this by some element of F0. So we get a well-defined element. And in fact, this classifies isomorphism classes. But what was this thing again? Remember, this was H1 Doram X over QP, dual, modulo F0, which was exactly, you could think of it as the dual of H1, but you could also say it's the annihilator of this. So it's just actually just isomorphic to functionals on differentials. So in this language of filtered phi modules and Galois representations, we've got a map from p-adic points to functionals on differentials, and it is exactly the common integral map we defined before. So more generally, we could do this for the fibers of En. So let's say that the fixed extension of filtered phi modules with graded pieces well, I'll just introduce notation for them. QP Vitoram. We saw the first one was Vitoram 2, and then we'll just pull it all the way up to Vitoram n. So where Vitoram I is a quotient of, how should you think of this? Just a quotient of the ith tensor power of Vitoram. Or I guess another way you could say it is that the filtered phi module, I tensor power of the filtered phi module associated to the Giordani module of the Jacobian forecast. So again, you can show that, again, this is something to do with Frobenius eigenvalues. So for any two mixed extensions, filtered phi modules, call them, oh, sorry, with graded, these V-ram i's, call them E and E prime, there exists a unique phi equivariant ISO. Well, so it's not, well, I guess maybe it's better to call it, there exists a unique isomorphism of mixed extensions of phi modules. So that's the analog of a splitting. So it's an isomorphism of phi modules, which respects these, not the filtrations, Hodge filtrations, but the filtrations coming from its structure as a mixed extension. And on the associated graded, they're just equal to equal to 1. So if you wrote them in matrix terms, it would be some isomorphism which was one's in block matrices, one's down the diagonal. And it turns out that you apply this to say E equals Z1 star of En and E prime equals Z2 star of En, the isomorphism you get is exactly the one coming from this Coleman parallel transport. Which again, you could phrase this in terms of Coleman sections, but maybe because it's not quite where I want to go, I'll just be brief and more later. So what this means is that I could have phrased everything I said about iterated Coleman integrals just in terms of this language of phi equivariant isomorphisms of mixed extension. And that was on this connection En, but actually, maybe I didn't quite spell this out, but the universal property of En means that Coleman integrals on this, or Coleman sections on this, determine all Coleman sections. That was a consequence of functoriality. So really, the whole theory of iterated Coleman integration you can describe in terms of this phi equivariant isomorphism. Okay, so I'll give a little bit more generality, and then I'll give some examples more relevant to p-adic heights. So I mean, I think I've thrown a lot of definitions at you with this mixed extensions. Is there anything that's not clear to anyone about what the objects are that we're considering? I haven't said anything about the global, yeah. So I'll say a bit more about the global Galois representations in a second. Yeah. Oh, you mean the description, a classification of all the isomorphism classes of mixed extensions with n-graded pieces? Yeah, so that's just what I'm about to do. Okay, yeah. Great question. That wasn't a plant, I promise. So to describe that classification, maybe let me introduce some notation. Say we could take the trivial mixed extension. So this works in much bigger generality than this example, but let's just. So I've started calling V to RAM, sorry, V to RAM is just V to RAM 1, and QP is V to RAM 0. Just let's see. Trivial mixed extension with those graded pieces, and then I'm going to define a group. V to RAM I. to be the group of, sorry, what to be the unipotent group of isomorphisms of this trivial mixed extension VDRAM I, as where we're not asking they respect any structure except the filtration. So they don't have to respect the Hodge filtration or the Frobenius. So if we could phrase that in my silly language of mixed extensions as a mixed extension of QP vectors. Right, so they're exactly, again, testing on working lower triangular. These really are just, you know, isomorphisms of this vector space, so block matrices, which are just this block matrix net. So this is going from V naught to VDRAM naught to VDRAM net. Okay, and then inside here, I'm going to define subset F naught to be the subgroup where we ask them to maybe behave a little bit more nicely. The unipotent subgroup of automorphisms which respect the Hodge filtration. So I guess strictly respected. So they have to send Fi to Fi and so on. Okay, so now I can answer Davide's question. You can do the exact analog, but maybe it's not surprising. You no longer get something which gives you a vector space or even a group. So extensions of filtered fine modules we classified in terms of a vector space. And that makes sense because you can add one extension and linearly compose them by this usual kind of bare extension construction. But mixed extensions with two pieces, you can't add them. So actually, to go back to Samuel's talk, they actually mixed extensions, sorry, not two graded pieces, three graded pieces, I suppose, V0, V1, V2. The set of isomorphism classes of mixed extensions is actually a bi-extension. So if you fix one extension, then you can add when you vary the other one, or the same the other way. And then there's some compatibility. There's an action of X, V0, V2, but there's no group law in the whole space. And I'll come back to this bi-extension point. So then lemma, this set of isomorphism classes of VDRAM I. So maybe it's not obvious immediately from the definition, but it actually has the structure of a scheme, and we can describe that scheme, well, actually a variety of a QP as a coset space. So it's isomorphic to the coset on the right, F naught modulo U of VDRAM. So this is like the non-abelian analog of VDRAM. So when n equals 1, this U of VDRAM I is just VDRAM 1. And then we quotient by F naught to get the space of mixed extensions. Now we get this coset space in a unipotent group. So the proof is exactly the same. So I just said, we're given E in here. The unique isomorphism of mixed extensions of mixed extensions respecting phi. And choose SH. Oh wait, have I done this the opposite way around to the way I did? Sorry, yeah. So I don't confuse my notes, sorry. Here. Then SH inverse composed with S phi gives us an element of U. And well, this S5 was God-given, but this SH involved a choice. But if we change SH, then this will just change that element by the left action of F0. And that's what gives this classification. Okay. So now I'm going to say a little bit about the Galois representation side, the global Galois representation side. Just give an example. So maybe first I should just at least make a remark about why do we get a map from rational points to these mixed extensions of Galois representations? Well, it comes from unipotent étale fundamental groups. So mixed extensions of PK reps. Series. Oh. But it's a big black box that I haven't spoken about in these lectures. And then the fact that when you apply d-Chris to this construction, you get back this relation to En Duram, En, tablet n, via this mysterious function. I mean, this is a hard theorem of awesome. In a good reduction case. So I guess, yeah, P was meant to be good reduction. Yes, yeah, that's a way to get a Galois. I mean, that's, yeah, this is the funny thing is we don't actually know how to, I guess it was a bit like when I mentioned in the Zilber-Pink conjecture, this notion of special points. So we're applying this notion, but we're not actually, we're forgetting that the modular curve already has a notion. I guess it's kind of because we don't know how to use that. No, this hasn't used, this is all general. I haven't used any. I mean, I think in the Lawrence Venkatesh paper, they even discuss trying to apply their method to the S-unit equation with the Legendre family. And in their case, it doesn't work because in their case, there are too many isomorphisms to filter by modules. Slightly different. Okay, but so how can we describe now isomorphism classes of Galois representations? So now let's V naught Vn be some G reps for some group G. Then we can similarly define this group U of V naught to Vn. And this is now a unipotent group with an action of G. So we can talk about its non-abelian cohomology. And that's another way of interpreting what this set of mixed extensions is, which, depending on your taste, is either better or worse, or I guess the same. And also, Kim developed a very nice theory. So this is if Hom Vi Vj, the equivariant Homs equals 0 for all I less than j, and some finiteness assumptions on G. Okay. So for example, I'll give examples when they're satisfied. So it implies that this is actually algebraic, so this is actually represented by a scheme over Q. And the precise notion of how you make sense of it being representable, what the functor is you want to represent, I won't go into. Okay, so now maybe I just want to specialize to the example related to quadratic Chabauty. Actually, no, maybe I'll just make one more remark about the general case. So we have some, returning to a case of a curve, projective curve X over Q, we have some crystalline GQ reps. One the n, and some map xk to m dk v naught up to the n, or k of q. And well, in some nice, if we can add some conditions, then we're saying that this is actually mapping into the QP points of some variety. And then what we want, so what we want to do is we want the image of, so we want to get an abstraction to a p-adic point coming from a local point, sorry, from a global point rather. The image of mixed extensions of GQ representations into this space of filtered prime modules. So these are now both schemes over QP. To be non-dominant. So, I mean, I haven't actually told you that these are both schemes over QP, but I haven't told you that this map is actually algebraic, but it is. That's another thing that Kim shows. And before I go to the case of p-adic heights, maybe I should say, why should this be true in general? So actually, this space of Gauss representations, we can actually almost restrict to the space of, restrict to space of mixed extensions which are unramified outside a finite set of primes T. Finite set of primes. And they're crystalline, which is what the F says. And so what does this space of mixed extensions look like? You can describe it, it's, so in particular, I guess you can say the dimension of this space, lots of letters now. Sum over all I less than j of the dimension some block-Carto Selma group. Which again, it's a bit of a black box. But so I mean, the relation between this and this is really just from how you can describe this space of mixed extensions. With a bit more time, it would be straightforward to describe why this was true. On the other hand, we've seen that this dimension of this is actually exactly equal to the sum over I less than j, the dimension of H1F EQP, VI dual T sub Bj. So why should we expect that, that this dimension is smaller than this dimension? So this is actually, well, I mean, ultimately, we don't know that this method produces a finite set of p-adic points in general. So maybe it's a bit much for me to say why it should be true, because we don't actually know, but we do know that it's implied by kind of a certain special part of the block-Carto conjectures on Selma groups and special values of L functions. They're ranks of K groups. So I guess it's if j is greater than I plus 1, then the difference in dimension between these two will tend to be j minus the dimension of 1 GQ. So you should think of this difference of dimension as being some kind of non-abelian avatar of this, well, I guess genus minus rank. You know, in dimension 1, we wanted, in rank 1, we wanted genus minus rank to be big. We want the rank to be small relative to the genus. But we know that can be hard because, you know, Jacobians can have, you know, it's hard to say what ranks of Jacobians can look like. You know, abelian varieties can have big ranks. But in this kind of case where j is greater than I plus 1, Bloch-Carter conjectures actually predict, this is following on from Beilinson conjectures, they predict that we actually know exactly what these ranks are. They're not mysterious at all. And actually, the dimension, it says it should be equal to, so I guess, yeah. So this thing is a Galois representation. We just take the invariance and the complex conjugation. And then we can also take the invariance after we twist by -1 under the whole of the Galois group. So both of these things are actually very easy to compute. So if we could just, or if someone else maybe, we can't, but I mean I can't, but if someone else would just prove the Bloch-Carter conjectures, then we could really get going and study lots of examples. And maybe actually, so this part of the Bloch-Carter conjectures about describing these dimensions is one case where in the world of modular forms, a lot more is known. So in depth 1, these Galois representations are just coming from modular Jacobians. But in depth 2, the Galois representations you're seeing are coming from Rankin-Selberg convolutions of weight 2 modular forms. There's been a lot of activity on Bloch-Carter Selmer groups of these. Okay, so now let me specialize in the last few minutes to p-adic heights. And in particular, so I already mentioned Neckar-Barr p-adic heights. So what are p-adic heights? So p-adic heights are exactly, in the language of Neckar-Barr, saying to someone the other day, there seem to be as many notions of what a p-adic height is as there are papers on p-adic heights, almost. So a local p-adic height, so Neckar-Barr's local p-adic heights are you can actually, he doesn't exactly, I mean, he doesn't use this exact language, certainly doesn't mention non-abelian group cohomology, but they're really just functions, algebraic functions, HV, so I guess from M PQV, QP, I guess I was calling V1, QP1, 2QP. So this is for V not equal to P. And then when V equals P, it's an algebraic function, HP, MGQP. So, but where we impose that they're crystalline, so he also does a semi-stable version, but we'll get into that. QP, which remember, this is the same as mixed extensions of filtered Phi modules. QP1. And just to emphasize, so what's V1? In our notation, V1 is the p-adic tape module of the Jacobian, so it's QP tensor PPJ. But he does this for a general abelian variety, and actually even more generally for height pairings on algebraic cycles. And this depends on a choice of the splitting of the Hodge filtration, which also came up in Samuel's talks. And well, actually, this is not so hard to define. That's essentially coming from the fact that you can show using, well, so, I mean, it's hard in the sense that the proof uses the weight monodromy conjecture for abelian varieties, which is known, but I mean, when you use that, then you know that this is just actually the same as H1, PPV, PP1, which is isomorphic. And this thing, remember, we actually explicitly described it, you know, as just a quotient of this unipotent group by a filtration. And basically, you can imagine if you choose a splitting of the Hodge filtration, then you can kind of trivialize that quotient. That gives you the way to define this map. So I mean, yeah, he doesn't, in his paper, he doesn't mention this U mod F naught, but that U mod F naught is a nice way to kind of understand why you get this function. And what do these functions satisfy? Write it here. I won't go through all the properties, but M is a EQ mixed extension. Then sum over all V of HV of M only depends on the image of M in extensions of QP by V1 and extensions of V1 by QP1. And actually it defines, which is the same as, these are dual, so this is just the same as this squared. And actually it defines a bilinear pairing on these pairs of extensions. So it defines a height pairing on a global extension, but not bilinear. And so this actually gives you a reciprocity law for these mixed extensions. Gives this condition of being bilinear globally, but not locally, gives you an equation which is a condition for a collection of local Gauss representations to come from a global Gauss representation. And then via the machine that we've just described, this gives a reciprocity law in the language of Kim for x of q inside XQB. So maybe just the very last thing to say is that if we take this example, which I did at the beginning of this connection E on x naught to 37, so this actually defines a filtered phi module with graded pieces QPV and QP1. And the reciprocity law that you get from this, so it turns out there are no other local terms, so the height pairing just involves this, gives an equation. So this reciprocity law actually computes. So, well, we said that this was rank 0, the Jacobian for this, but this computes the rational points in QI. So this was from quite a while ago, a paper of Jennifer and Stefan Miller. And yeah, I think I'll end there.
Any questions, comments? Samuel?
So I'm not sure. So this, so for n equals 1, m q, I guess with an f, qp v1 is the same as h1f V1, which is the same as the QP Selma group of J. So actually, technically, this is one of the another annoying subtleties in the theory is there are two different definitions of like these XQPNs and these these obstructions to rational points, and they depend on whether or not you work with the Selma group or the points on the Jacobi. So, and sometimes some theorem will, actually I got an email about this the other week, someone asking about taking a paper. Sometimes a theorem will, use one definition when it meant the other one, and then it should have an assumption on finiteness of the Tate separated group. Does that answer you?
Any more questions, comments? So then let's thank Netan for his wonderful set of lectures and for the marathon lectures, in fact. 3 hours on behalf.
I think you were the ones doing the marathon.
Yeah, so on behalf of all the participants and the organizers, I would like to thank Netan once again. So please join me in thanking him.